Okay, so, when you're working with these embedded systems, you've got the software side of things.
Right.
And then you have the hardware, the physical chips and circuits.
Yeah.
And it's easy to kind of think of them as these separate worlds.
Right.
But the question is, how does the software actually know what hardware it's dealing with?
Right.
Like, how does it know what's out there, how to talk to it? It can feel a little bit like a black box sometimes.
It does.
So today, we're going to crack open that box and really try to understand this connection by looking at something called the device tree.
Okay.
So think of this as our guide to really getting how the software sees and interacts with that hardware.
Yeah, absolutely. And I think for anyone who's working with embedded Linux,
Yeah.
this concept of the device tree is fundamental.
Right.
It really is the core of how the hardware gets described to the software. And for this deep dive, we've got a really great resource to help us break this down.
Yeah.
It's a presentation called Device Tree 101, and it's by Thomas Pettazzoni.
Who is the CTO of Bootlin, a company that specializes in embedded Linux.
Very cool.
And Thomas has this wealth of experience. I mean, he's a major contributor to the Linux kernel itself.
Wow.
And he's also a co-maintainer of Buildroot. So
Nice.
we're really getting insights here from someone who's deeply involved in this world.
That's great. And the way the source material is laid out, I think, is going to really help us guide this exploration. It's in a slide format, so it's very structured. It's very informative. I think it's going to really help break this down in a clear and logical way.
Definitely.
So what we want to do today is really extract those core concepts of the device tree.
Right.
Why is this thing necessary? How does it actually work? It's magic. And why is it so important in this whole embedded Linux ecosystem?
Yeah.
So think of this as your kind of like fast track to understanding this area.
Okay.
So to kick things off, maybe you can set the scene for us. Why do we even need a device tree in the first place? What's the problem it's trying to solve? That's the essential starting point, right? So if you think about some of the hardware interfaces we work with, like, PCI Express you've got in your computer,
Right.
or USB, these have built-in mechanisms for discovery.
Okay.
So the system can actually go out and interrogate the bus and say, hey, what devices are connected here?
Right. So like when you plug in a new, mouse or keyboard or something.
Exactly. And it can figure out, oh, this is a mouse. This is how I talk to it.
Yeah, it just kind of works.
That's right.
Yeah.
But then you have a whole other class of buses and peripherals.
Okay.
Things like, I2C or SPI or various memory-mapped controllers. And these don't have that same discovery mechanism.
Okay.
The system can't just ask them, hey, what are you...
So it has to know beforehand.
It has to have this prior knowledge of, hey, I know there's a device here, and this is how it's connected into the system.
Right. So it can't just guess that maybe there's a temperature sensor at this particular address.
Exactly right. It can't make those assumptions.
Yeah.
So you need to actually describe this to the system in detail.
Okay.
So, think about it, even from the very beginning.
Yeah.
How many CPU cores does your SoC have? Where in the memory map are the registers for, say, the serial port?
Right.
Which interrupt line does it use to signal the processor? If you have an I2C controller, well, where are its registers? What interrupt does it use?
Okay.
Where does its clock signal come from?
Right.
And then you start getting into board level components, right?
Yeah.
So if you have, say, an audio codec on your board, something like a CS42L51,
Okay.
you need to specify, okay, well, what's its I2C address?
Right.
Which audio interface on the main chip is it connected to? Maybe even which GPIO pin do I need to toggle to reset that audio codec?
Wow. Okay.
So all of this needs to be explicitly laid out.
It's like this manifest of all the hardware that's in there that the system needs to have.
Exactly. It's this fundamental knowledge that the system needs.
Yeah.
Because without it, the operating system or the bootloader is just lost when it comes to actually interacting with the hardware.
Yeah, that makes total sense.
Yeah.
So historically, how did embedded systems handle this before we had the device tree? Was there just a bunch of custom code for every board?
Yeah, so historically, the most common method was to really just embed this information within the operating system or the bootloader code.
Okay.
So you'd have, C data structures and things like that.
Okay.
That would basically just spell out all these different components.
All right.
So you'd have, a block of code for board A, a block of code for board B.
Okay, so it could get messy real quick.
It did, especially as platforms became more complex.
Yeah.
So particularly on ARM32 architectures, as we had this explosion of different boards and devices,
Right.
this approach became really unsustainable.
Yeah, I can imagine.
The code size explodes, the potential for errors increases.
Right.
It just became really difficult to manage.
And to maintain, I'm
You-
sure. So what other solutions were there that led to the device tree? Like, did anything else pop up?
So one approach that you primarily see on by86 systems,
Right.
and also on some of the larger ARM64 systems, is using ACPI tables.
The ACPI, okay.
So these tables are provided by the system's firmware,
Mhm.
so the BIOS or UEFI,
Okay.
and they basically contain a description of the hardware.
Yeah.
And the firmware then passes this information on to the operating system.
So the firmware handles that description and just hands it over.
That's right. But for a lot of embedded systems, especially smaller ones or systems with different boot sequences,
Right.
ACPI wasn't really the best fit.
Okay.
And this is where the device tree really emerged as a more elegant solution.
All right, so is this something that was like invented specifically for Linux or
So the device tree actually has its roots in something called open firmware,
open firmware?
which was originally developed by Sun Microsystems
Okay.
for their SPARC and PowerPC architectures.
Interesting.
And as a side note, this is why you often see the prefix of.
Right, I was going to ask about that.
In function, names and variables related to device trees in Linux and U-boot,
Right.
that of stands for open firmware.
So it's this historical remnant.
That's right. Yeah, it wasn't initially developed specifically for Linux.
Okay.
But over time, it proved to be such a powerful way to describe hardware
Mhm.
that it's been widely adopted across a ton of different architectures that run Linux.
Yeah.
So you'll see it on IRC ARM64, RESCV ARM32, PowerPC Extensa MIPS.
Wow, that's a lot.
Really underscores its importance.
Yeah.
And in fact, if you're bringing up Linux on a new board today,
Yeah.
writing or modifying a device tree is almost certainly going to be a step you need to take.
Oh, definitely. So we've talked about the why.
Right.
Let's get into the how. So how does this thing actually work? Like, how do we go from, describing the hardware to having the system actually understand and use that information?
So the process starts with the developer
Okay.
creating a human-readable description of the hardware. And this is stored in what we call a device tree source file or a .dts file. So this .dts file is essentially a text-based blueprint of the hardware.
So it's like a configuration file, but more comprehensive.
That's a good way to think about it.
Okay.
So this .dts file is then processed by a tool called the device tree compiler, or DTC. And this compiler takes that .dts file, checks the syntax, and converts it into a more compact binary format
Okay.
called the device tree blob, or .dtb file.
Okay.
And sometimes you'll hear this also referred to as the flattened device tree, or FDT, once it's loaded into memory.
Right. Blob. It sounds very technical. What does this .dtb file actually contain?
So the device tree blob is essentially a highly organized binary representation of that hardware description.
Okay.
And it's structured specifically so that the bootloader and the operating system can efficiently parse it.
Okay.
And interestingly, despite holding all this information, these .ttb files are actually pretty small.
Right.
They're often only, tens of kilobytes.
That's surprising.
Yeah, and in the slides, there was an example using the DTC tool just to kind of illustrate this process.
Yeah, I was going to bring that up.
So the example show, you've got your .dts file and you run the command dtc-i dtbao btbo food.dtb food.dts.
Okay.
And that takes the human-readable device tree source, IODTS, specifies the output format as a device tree blob AODTB,
Okay.
names the output file food.dtb, and then points to the input.dts file.
Gotcha.
But what's also really useful is that you can actually reverse this process.
Oh, cool.
So if you have a .dtb file, you can decompile it back into a .dts representation.
Oh, that's handy.
Yeah, it's really useful for inspection.
Yeah.
So you would run dtc-idtb-odts food.dtb.
Okay.
And that'll give you back a human-readable version.
That's really useful.
Definitely.
So now we have this .dtb file.
Right.
What happens to it? Like, how does the operating system actually get access to it?
So this .dtb file needs to be made available to the operating system during the boot process.
Yeah.
So one way to do this is to actually just embed the .dtb file within the bootloader itself.
Okay.
So you might see this in U-boot or barebox.
Right.
But the more common approach, especially for Linux, is to have the bootloader load the .dtb into memory
Good.
and then pass the memory address of the .dtb to the Linux kernel
Okay.
when it starts executing.
All right, and that's where that U-boot command comes in. Boots kernel add or DTB add.
Exactly. So in that command, you have the kernel address, which specifies where in memory the Linux kernel image has been loaded.
Okay.
And then you have the DTB address,
Right,
which
yeah.
is the memory address of the device tree blob.
And that dash in there just means no RAM disk or...
Yeah, that's right, when there's no initial RAM disk.
Okay.
And critically, the bootloader needs to communicate this DTB address to the kernel somehow. And it does this by using a specific CPU register.
Okay.
So for example, on ARM32 architectures, this is often register R2.
So it's like right there at the start, the kernel knows, here's where my hardware description is.
Exactly. It has that information immediately available.
Yeah.
And it's worth noting that bootloaders can sometimes make small modifications to the DTB in memory before handing it off to the kernel.
Interesting.
So things like adjusting memory parameters or passing boot arguments. And then once the kernel is running it, and even user space tools can parse and interpret the information within the DTB using libraries like libftt or even custom code.
All right, so now that we have that overview, like where do we actually find these .dts files in like a real-world project? Is there like a central repository or?
So ideally, there would be a single central repository that would contain device tree source files for, all kinds of projects.
That makes sense.
It's been discussed, but it hasn't really emerged. In practice, the closest we have is the Linux kernel source tree itself. So under the directory arch boots.
RCH being the architecture.
That's right. So you'll have ARM, ARM64, RISC, PV, whatever the architecture is. And there are literally thousands of these files.
Really?
In Linux kernel 5.10, there were over 4,700 .dts files.
That's crazy.
It really highlights just the sheer amount of hardware that Linux supports.
Yeah.
And since bootloaders like U-boot and Bearbox need these descriptions too, you'll often find copies or synchronized versions of these .dts files in their source trees as well.
Makes sense.
So in the slides, there's a good example using the STM32MP157ADK1 development kit. That really illustrates this.
Could you walk us through that?
Sure. So in that case, the device tree actually comes into play at a few different stages of the boot process. So in the very early stages, involving trusted firmware A or TFA, you might have a device tree source file there in the TFA source code. And when you build TFA, this .dts file gets compiled into a .dtb file. And that .dtb file is then incorporated into the firmware image that TFA produces. Then you have U-boot, and U-boot will also have its own .dts file for that board. So when you build U-boot, it'll compile its .dts into a .dtb and embed that in the U-boot binary. And then finally, the Linux kernel will have its own device tree source file for that board. And that'll get compiled into a .dtd along with the kernel image.
So it's not just like one device tree for the whole thing.
That's right. Each component in the boot chain might have its own device tree tailored to its needs.
Gotcha.
So the slides even showed a snippet from a U-boot boot log demonstrating how this works. So you see U-boot loading the kernel image and the .dtb file into memory. And then it uses that boots command to start the kernel and tell it where that device tree blob is located.
Very cool. So that gives a good picture of where these files are during development. But once Linux is actually running, can we see that device tree?
Absolutely. So Linux actually exposes the device tree of the running system through this special virtual file system. And it's mounted at sysfirmware device tree base. And within that directory, you'll find a representation of the entire device tree structure.
Cool.
And it's all represented as files and directories. I mean, each node in the tree becomes a subdirectory. And the properties of each node are files containing the values.
That's a great way to actually look at how the system is seeing the hardware.
It really is, yeah.
Wow.
And if you happen to have the DTC tool on your target system, you can actually decompile this file system representation back into that .dts format. Using the command dtc-ifs sysfirmware device tree base.
Very cool.
So that can be incredibly useful for debugging or just getting a clear view of exactly what device tree the kernel is using.
Yeah, that's really neat. So we've covered what it is, why we need it, where we can find the files now. Let's get into the actual device tree source file itself. What does it look like? What's the basic syntax?
So at its core, the device tree is a tree of nodes. And each node represents a device or a functional block of hardware in the system. And these nodes can contain properties, which are key value pairs that describe the characteristics of that device or block.
So each hardware component gets its own branch or leaf on the tree.
That's a good way to visualize it.
Yeah. And then its attributes are the properties.
Precisely. And within these property values, we have the concept of cells. So a cell is just a 32-bit unsigned integer. And this allows the device tree to represent a variety of data types.
code?
So, for example, if you need to describe something bigger, like a 64-bit memory address,
Right.
you would use 2 consecutive cells.
Gotcha.
And then we also have things called handles.
Handles.
So these are unique identifiers that are assigned to different nodes in the tree.
Okay.
And they essentially act as labels that allow other nodes to reference them.
So they're kind of like pointers within this hardware description.
Exactly.
Yeah.
And this allows you to create, cross-references within the hardware description itself.
Okay, that makes sense. So one thing that's important to keep in mind is that the device tree compiler, the DTC,
Right.
it does check the syntax of your .dts file, make sure that it follows the correct structure and all of that.
Yeah.
But it doesn't actually do any semantic validation.
Right. So it checks that the language is correct,
Yeah.
but it doesn't necessarily check that your description of the hardware is accurate or makes sense.
Right. So the compiler understands like the grammar of the device tree language.
Yes.
But not the underlying specifications of all the different hardware.
That's exactly right.
Okay, that makes sense. And I think the slides have a simplified device tree structure, just to give people a sense of what it looks like. So I'm looking at that now.
Yeah.
What are some of the things that stand out to you?
So I'm looking at that as well.
Okay.
At the very top level, you have the root node
Right.
represented by, and this has a bunch of important properties.
Right. It's got hashtag address cells, hashtag ed size cells.
Right. Those define how addresses and sizes are defined within the device tree. You've got model, compatible.
Compatible seems very important. Yeah.
Absolutely. And then within this root node, we have a number of child nodes.
Yeah, like caucus, memory at 0.
Yes,
Jobs, interrupt controller at sitter is 0, 0 to 1000.
Stop it.
Socket skier. And some interesting symbols in there too, right?
Yeah.
You've got the adder in those names.
Colons. Yeah.
Colon in story.
Yeah. What are all those?
Right, so let's break those down. So the hashtag address cells and hashtag size cells in the root node
Okay.
that basically define how many 32-bit cells
Okay.
will be used by child nodes to specify the address and size in their reg property,
In the reg property. Yeah.
which we'll talk about more in a bit.
Gotcha.
The model property just provides a human-readable identifier
Right.
for that specific hardware.
Okay.
And then compatible, as you pointed out, is really crucial.
Yeah.
That's a string or list of strings
Okay.
that identifies the device or the board, and it's used by the operating system to find the appropriate driver.
The appropriate driver. Gotcha. Okay.
And the @ symbol in a node name, like memory at 0.
Right. That indicates what we call a unit address.
The unit address, okay.
And this is often used for devices that occupy a contiguous range of addresses.
Okay.
And the number after the @
Yeah.
is typically the starting address of that range,
Yeah.
which will be defined in the device's reg property.
Okay, that makes sense.
And the colon in Intura, that's actually introducing a label.
A label.
Yeah, so intrac in that case is a symbolic name
Okay.
that can be used to refer to that specific interrupt controller node.
Gotcha. So it's like a named reference.
Exactly.
Very cool. And then we see all these other properties
Right.
within the nodes, like compatible, again, clock frequency, device type, reg. It seems to be for register addresses. And then you see under the sock node all these other nested nodes, like I2C1, Ethernet.
Right, and those have their own properties and potentially even more deeply nested nodes.
Yeah, like CS42, all 5-on-1.
Yeah, you can really see the hierarchical nature of how the hardware is organized.
Like a hardware family tree.
Yeah, and the nesting reflects that organization. So for example, I2C1 and Ethernet.
Right.
Those controllers are typically integrated within the SoC itself.
Right.
So they are children of the SoC node.
Makes sense.
And a device like the CS42 All51 audio codec would typically be connected to an I2C bus.
Right.
So its node is a child of the I2C1 node.
Yeah, makes sense.
And then you've got properties like interrupts and interrupt parent, which are obviously important for describing how devices signal events via interrupts.
Right.
And you'll see a status property as well,
Yeah.
which indicates whether the device is enabled or not.
Okay.
And in the chosen node,
Right.
we'll often see a statoutpath property.
Okay.
And that's used by the bootloader or kernel to determine where console output should go.
Very interesting. Okay, so there's a lot of information in these device tree files.
There's a lot of detailed information.
Yeah. So how do we manage this complexity? Is there a way to like break things up?
Yeah, absolutely. So device trees actually support a mechanism called inheritance. And this allows you to split your device tree description into multiple files
Okay.
and include them within each other.
That sounds useful.
It is, especially when you're dealing with complex SOCs that are used across many different boards.
Right. You don't want to repeat yourself over and over.
Exactly. So you'll often see a distinction between files with the .dtsi extension and .dts.
Okay. .dtsi versus .dts.
So .dtsi files include files.
Gotcha.
They're not intended to be compiled directly.
Okay.
They contain definitions that are common to all boards based on a particular SO.
So it's like the SOC level description.
That's right.
Okay.
So things like register definitions, interrupt controller configuration, that's all in the .dti.
Okay.
The .ts file, on the other hand, is the final device tree source file.
Okay.
That describes a specific board.
All right.
So it will include one or more .dtsi files to inherit that base description and then add board-specific details, like external peripherals and their connections.
So the .dti is the foundation,
right,
and the .dts builds upon it.
Exactly. And the way inclusion works is essentially by overlaying the tree structure from the including file onto the tree structure of the included file.
Gotcha.
So the board-specific .dtts can override values or add new nodes and properties to the base description.
Okay.
And this inclusion is typically done using the C preprocessor's hashtag include directive.
Okay.
So the slides actually had a good example of this with a sock.dtsi and a board.dts file.
Right, where they enabled a UART.
Right. So the sock.dtsi might define the UART with, its compatible string register base address and maybe a status of disabled.
Right.
And then the board.dts file, by including the sock.dtsi, can then target that UART node and change its status to, to enable it for that particular board.
Okay.
And the slides also emphasize that the preferred way to do this is by using labels.
Labels.
So in the .dts file, you can define a label for a node. For example, usart1.serial@dia.
Okay.
And then in the .dts file, you can refer to it directly. Using an ampersand followed by the label.
Okay.
So like in usart1 to modify its properties.
Gotcha.
And this approach is generally cleaner and more maintainable than, reopening nodes based on their full path.
Right.
And this is actually heavily used in the support for STM32MP1.
Okay.
Within the Linux kernel, for example.
Yeah, that makes a lot of sense. And it's a good way to promote code reuse across different boards.
Exactly.
Yeah. Cool. So when someone is creating a device tree, are there any design principles or best practices they should keep in mind?
Yeah, absolutely. So there are a few key principles that can really help guide the creation of effective device trees.
Okay.
And the first one is to describe the hardware as it is.
Okay.
Not how you intend to configure or use it.
Okay.
So the device tree should be a factual representation of the hardware connections and capabilities.
Gotcha.
Not a reflection of a specific software configuration.
So you're describing the potential of the hardware.
Yeah, you want to be as generic as possible. The second key principle is OS agnosticism.
OS agnosticism.
So ideally, the device tree description for a piece of hardware should be the same regardless of whether you're running U-boot FreeBSD or Linux.
Right.
You shouldn't need to change the device tree just because you're changing the OS.
That makes sense.
And the third important principle is to focus on describing the integration of hardware components, not the internal workings of those individual components.
Right.
So the device tree is concerned with how a device is connected to the rest of the system. So things like what interrupt lines, it uses the DMA channels, it can access its clock sources, its reset signals.
Gotcha.
But the internal details of how that specific device works, that's the responsibility of the device driver in the operating system.
That makes sense. So it's about the connections between things, not the internals of each thing.
Exactly.
Okay, so those are some good guidelines, but how do we know if we're doing it right? Are there standards or rules beyond just the basic syntax?
Yeah, so this is where the device tree specifications and device tree bindings come in.
Bindings.
So the device tree specifications, which you can find at devicetree.org.
Okay.
They define the fundamental syntax of the device tree language.
Okay.
And they also define a set of standard properties that are commonly used.
Okay.
But the specifications alone aren't enough.
Right.
There's such a wide variety of hardware out there.
Yeah, you need something more specific.
Exactly. And that's where device tree bindings come in.
Okay.
So these are documents that specify precisely how a particular type of hardware should be described in the device tree.
Okay.
And you can find these binding documents within the Linux kernel source tree.
Okay.
in the documentation device tree bindings directory.
Gotcha.
And these bindings actually go through a review process by a dedicated team.
So it's like peer review for hardware description.
It is, yeah. They make sure that things are consistent and accurate. Historically, these bindings were often written as human-readable text files.
Right.
But the current trend is to use YAML, which is more structured and machine-readable.
Right.
The slides showed examples of both, actually.
Yeah, I noticed that.
An older-style text binding for a SPEAR SMI interface, and then a newer YAML binding for an STM32 I2C controller.
Okay.
So these bindings will typically outline the required properties, things like compatible reg, interrupts,